class. So for this lecture, we're looking over section 2.7 in your book, and this is the inverse functions. Okay, so notice there's a lot of things going on here, isn't there? So before we actually get to going over each and every sentence of what you see thus far, what I'm going to do is I'm going to go ahead and tell you just kind of what an inverse function is and what it does. Okay, so just to let you guys in on something, the idea of inverse functions is exactly what the name says it is. It's an inverse of something. It's basically unraveling something. It's doing the opposite of what you would be doing. So the inverse of multiplication is division. The inverse of subtraction is addition. The inverse is of addition and subtraction, and so on. So it's kind of the opposite, okay? So when you're looking at a function, and the function, says that you're multiplying by something, then you're adding by another number, then the inverse would mean that you're dividing by a number, and then you're subtracting by something. So you're basically getting a particular number, but then unraveling it and going backwards to get the same number that you started with, okay? So that's the idea behind inverse functions, because y'all know what a function is, right? Remember that a function has to, for every x, has to have exactly one y value, not two y values, not zero y values, and so on. And then there's the vertical line test that shows that. So in inverse functions, there are rules as well. Okay, so in order to go from a function to an inverse function, there has to be this idea of this one-to-one correspondence. Okay, so for an inverse to even exist, so I'm just going to underline the important stuff right now. So for an inverse to exist, oops, don't want to write with a crayon, I want to write with a pen. So for an inverse to exist, the function has to be one-to-one. Okay, and we'll go over that momentarily. But what I want to do right now is this whole idea of one-to-one. Let's look at the shorthand for it. Okay, so shorthand for one-to-one, you probably won't see it in MLP, like as in your math book in general, but you may see the shorthand, on online resources like websites. You also might see shorthand in other books, or maybe some, manuals of some sort. So just to let you know that this is the shorthand for it, and it does exist out there. The notation for an inverse function is f to the negative 1, okay, or f to the negative 1 of x. So remember that what this means is that here, this means it's the inverse function of x, okay, meaning that remember that it's the inverse function, but everything's written in terms of x. So you have to caution yourself, though. Remember that what I said before is inverse means you're unraveling. This does not mean, so caution yourselves. F to the negative 1 of x does not equal 1 over f of x. That's something completely different. That means you just flip the fraction, basically. Okay. So make sure you understand that f to the negative 1 of x is the inverse function, not anything more. Okay, it unravels the regular function, and it's in terms of x. Okay, so here's these criteria that we must follow. So a one-to-one function, so here's what a one-to-one function means. One-to-one function means that for every value of x, there exists exactly one value of y. So that's the definition of a function. Okay, that's something we already know. It's from section 2.1. Now, part 2 of this is the criteria for being one-to-one, okay? So it means that for every value of y, there exists exactly one value of x. So it works the other way as a function does. So again, for every value of y, there's existing exactly one value of x. So not only that for every x, there has to be exactly one value of y, now for every y, there has to be exactly one value of x, okay? And this is the whole reason why, because we have to trace it back. Because a function goes forward to an inverse function, and then we have to be able to trace it back. Okay, so let me kind of make this a little bit clearer in your mind. Remember the kind of sets of the domains and ranges that we just went over when we first started looking at functions? I hope you guys do. Let me move this down a tad bit so we can have a little bit of extra room. Okay. So say, for example, that you have a 1 and that you have a 2. Okay. And here you have a 3 and a 4. Okay, so you've got your domain, and then you've got, your range. And remember, for it to be a function, each and every one of these guys had to have exactly one y value. And what I mean, each and every one of these guys, I mean each and every one of the x values had to go to exactly one y value. And so what's really cool about this is that notice that you can start over here. Remember, inverse functions are going to go backwards to the regular function. So you got, if you want to find the inverse, you can go from the function to its inverse, and then you should be able to travel from its inverse to the function, okay? So this means that you can travel backwards. You're like, oh, look, 3 goes to 1, 4 goes to 2. That's kind of the idea of inverse here. So we've got not only that this is a function, but it also has an inverse. This happens to be one-to-one. So there's one y for every x, and then there's one x for every y. Okay? Now, if you have the domain and then you have, let's see, 1 and 2, and then you have 3. So remember, for this was a function because this value of x goes to exactly one value of y. And this value of x goes to exactly one value of y. So it's a function, okay? But however, notice if I were to travel backwards, I would have two y values. Going back to two x values. So it's not one-to-one. At this point, we could call it 1 to 2. So we go 1 here, and then 1 here, and then when we try to go backwards, we have two values. So this is not 1-to-1, so this does not have an inverse. Does not have inverse. Okay, so yes, this right here is my shorthand for inverse. Okay, so remember, it has to have that 1-to-1 correspondence. Okay. So what's really interesting about this is that remember that functions pass what we would call the vertical line test. Now, for there an inverse to be existing, that means it has to be 1-to-1. Therefore, it has to pass now the horizontal line test. And it's the same exact way that you would do the vertical line test. It's just now, instead of vertical line, it's a horizontal line. That's the only difference. Okay. So we have this horizontal line test, and it states here that a function f has an inverse that's a function f to the -1 if there is no horizontal line that intersects the graph of the function at more than one point. So basically what that means is that if you draw a horizontal line through the graph and it crosses that graph more than once, notice I said more than once, so if it crosses it 2 times, 3 times, 4 times, at any point on there, then it does not have an inverse. Okay. All right, so moving forward, let's look and practice the horizontal line test. So what I'm going to do is I'm going to use, well, I guess let's use red. That will show up better. So my horizontal line test. Notice that all of them are functions. If I use my vertical line test, they all cross through one time. Every single time I would draw a vertical line. But now we have to see which ones are one-to-one, if an inverse could possibly exist with them. So if I draw my horizontal line, notice in this one I can draw my horizontal line all day long, and it only crosses through once. Okay, so we can say that this is one-to-one. So inverse exists. This one, however, notice it will cross through here. And this is a parabola, right? This is a function. We know this to be a function. But if we draw a horizontal line, it works for this one because it only crosses through once. But again, it only takes one time for it to cross through twice and it not contain a one-to-one. This does not have an inverse at all. So we can say that this is not one-to-one and an inverse does not exist. Inverse does not exist. D and E does not exist. So can y'all guess what this one is down here? Whoa, that just, well, at least it shows it. There we go. Crosses through 3 times here, doesn't it? So note that this is not one-to-one. So actually what I'm going to do is I'm going to do this. Copy. And then there we go. So the inverse does not exist over there. This one, whoops, inverse does exist because, again, I can draw a horizontal line through this all day long and it only crosses in one place each and every time. So here I can say that this is one-to-one and an inverse does exist. Okay. Okay, so now that we've figured out if an inverse exists or not and what an inverse function does, let's talk about this mathematically. Okay, let's talk about this looking at graphs so far. Okay, so basically, remember, if we're going from a domain to a range, that's a function. And going back from the range to the domain, it's the inverse function. So it would make sense that x's and y's switch, because even in the beginning when we saw, let me get back to it, this here, notice that I'm starting off with my x here for the function, and I'm ending up with my y over here for the function. But then if I'm going backwards, this now has to be my x, and then this goes to my y. Okay, so it has to have that one-to-one correspondence. So that means that what happens in an inverse is just simply the idea that the x's and y's switch places. Okay, so to go further with it, the x's become y's and the y's become x's. Okay, so looking at this, all of this over here is the function. So notice you have the function here, f of x. That's a function of x. And here you have the inverse function of x. Okay, so remember, inverse functions of x does not mean 1 over f of x. It means that these x's and y's switch places. So what you notice is that instead of the regular function having 6, negative 5, and this means that the inverse function is going to have negative 5, 6. And down here, if the regular function has 7, 4, then the inverse function has 4, 7. Okay. So it's just switching the x's and the y's. That's the only thing that you guys are doing. So Another thing what you'll notice is that in notation, it's pretty important to kind of get down in your head what happens with notation, okay? Remember that any time you have anything in the parentheses around a function notation, you know that that's the number that you're starting with. You know that that's the x, you know that that's the domain, right? Okay, so for this 6, here's the x, then that means f of 6 equals -5. So in the inverse function, notice the -5 is now the x, and the 6 is the actual value of that inverse function at 5. Sorry, -5. Okay. Same here. Notice we've got 7 for x, 4 for y. In the inverse function, you have 4 for x and then 7 for y. Okay. So what this means is that there is a particular place on a graph to where one number is always equal to the other, such as 0, 0, 1, 1, 2, 2, -1, 1, -2, -2, and so on. Okay, and that line is y equals x. Okay, and what's interesting about this line y equals x is that the inverse is reflected over that line. So we can see a regular function and its inverse on the same graph as long as it's reflected across that line. So if you're trying to draw the inverse, you can just reflect it right across that line y equals x, and we're going to practice that. But also to check yourself, you can fold the what you drew, that piece of paper on that line y equals x, and one side should equal the other. It's symmetry. Okay. So going on to the next one, actually I think we have some more down here. Oh, it shows a nice little picture here. So notice here that they say that this is the graph of your function f of x. This is a point on that particular graph, obviously, right? There's a dot, here's A, here's B, but then here is that line, y equals x, and then here is the inverse function. And notice my A became B and my B became my A. So the x's and y's switched. What you will also notice about this, and I don't know why this, hold on a second, y'all. That's odd that there's a line in the middle of it right there. Anyways, okay, just moving along. Pay no attention to this solid line right here. I don't necessarily know why it's there, okay? But what we want to do is we want to look at this y equals x. Okay, so the main thing here is that notice that every single point from this inverse function to this line y equals x is the same distance from the regular function to the line y equals x. Okay, so this means that even this point is the same distance to this point, and so on. This point is the same distance to that point. Okay. So notice in drawing it, if we were actually given just the graph of f, all we have to do is pick a few points along here and then just switch them. And then voila, we have our inverse function. Okay. All right, so let's practice on some of this. Okay, so just remember what we're doing. We're just switching the x's and the y's. So sometimes you'll notice that here's a point, here's a point, and here's a point. Sometimes those points are already labeled for you. Sometimes they're not. Sometimes you have to pick out a point, but that's okay. I think y'all are good at picking out points. Okay, so what I'm going to do is I'm going to look here and I'm going to write down these points. Okay, and I'm just going to go in order here. So I've got what? -3, 0. And then I have, actually let me leave some room here. And let's use a really cool color with it. Let's just use red. So here's the points on the function f of x. Okay, this is f of x. So we have -3, 0. We have -1, 2. And then our last little dot there is what? 5, 3. Okay, so for my inverse function, I just simply switch the x's and y's. So instead of -3, 0, I have 0, -3. Instead of -1, 2, I have 2, -1. Instead of 5, 3, I have 3, 5. So what I'm going to do is I'm going to plot these points here. And remember that this, like all these are in kind of order to where a line is drawn from this point to this point and then from this point to that point. And so we're going to go in the same order here. So we've got 0, -3. We've got 2, -1. And then have 3, +5. And notice the 5 isn't written up there, but that's really okay. All right, so drawing these, remember we went in order, so we have to go from 0, -3 to 2, -1, and then 2, 3, 5. And so that's exactly what I'm going to do. So 3 here, and from here up to here. And notice something else that I may be forgetting is that it looks like I stopped here, but notice on the regular function, I didn't stop there, did I? I have to keep on going with that. That's an arrow. So make sure that you keep on going, even though that it looks like it stopped, but remember that arrow means it keeps on going forever and ever and ever. Okay. So let's do this. Let's go ahead and I will draw the line y equals x, and I'll make it all dotted so it'll look nice. I don't know why it keeps doing that. Okay. So that's the line y equals x. And notice if I folded it across this line, these things are symmetric. It would look like one thing. Okay, so let's take a look at this next one. Here's our function f of x, and I'm going to have some points with it. Okay. So going from points, going over here to the left-hand side, notice that there are some points already made for us, and then something that happens over here. So we're going to have to go along with a description as opposed to a point, unless y'all want to deal with fractions and stuff, which I don't think you do, but I think if you just have the good characteristic with it, I think that will be good enough. So let's go from -2, 4. So we've got -2, 4. And then we've got -1, 2. And then we've got 0, 1. And so then also, I'm going to put a little tiny bit more in here because this is really interesting what happens to this graph over here on this right-hand side. Notice that it gets really, really close to the x-axis, but it doesn't touch it. So I'm just going to write this in words because I'm not going to plot points with it. I can, but a lot of times people don't like the decimals or anything, so I'm just going to go ahead and write down its characteristic on what it does. It gets close to the x axis. Okay. But notice it doesn't touch it and doesn't go to cross it. So what I'm going to do now is I'm going to plot my inverse function. So I know just based on the one previously that I had to just switch the x's and y's, so I'm going to do that. So instead of -2, 4, I've got 4, -2. Instead of -1, 2, I've got 2, -1. Instead of 0, 1, I've got 1, 0. And now, remember when my x's and y's switch? They're even going to switch in statements that I say also. So if it gets close to the x-axis on my regular function, if I switch the x's and y's, then it gets close to the y-axis on my inverse function. Okay, so we're going to be following along in this. So we've got 4, negative 2. So 4, negative 2. We've got 2, negative 1, 1, 0. And then it gets really close to the y-axis. So remember, I'm going in this order. So I start here, and I'm going along here, and it gets really close to the y-axis, but it doesn't cross it. And remember that this side actually had arrows on it, so I'm going to have to put an arrow on that one too. So notice not only can you use points, but you can also use statements and just change all of the x's to y's in your statements. And so here we've got our y equals x. There's our line. And of course, if we were to fold that, all those graphs would look like the same thing. If we folded it along the line, y equals x. So that's a graphical representation. So anytime that you graph these, pick out points of your regular function, switch the x's and y's, and then plot your inverse function. Okay. Next one. Now we actually have to take the mathematical approach and find this. Okay, so it says finding the inverse of a function. All right, so it does look a little bit wordy, but I think once you get your steps down, you'll be like, okay, this isn't so bad. What we're going to do is, first of all, notice that we'll replace f of x with y. So everywhere where you see an f of x, we put a y. We interchange the x and y's. So basically just switch x's and y's. Okay. And then solve for y. Okay, so let me shorten this up for you. Replace f of x with y, switch x's and y's, and solve for y. Okay. So yes, this goes into a huge explanation of something, but just know that in order for you to find an inverse, you know how an inverse exists. Because remember that it can't exist if it's not one-to-one. So you have to know that something's a one-to-one function before you actually start finding the inverse of it. Okay? This is a one-to-one function. Oh, by the way, before I go on, we didn't discuss number 4, and we're going to after we find the inverses of stuff. Okay, this is where you actually are able to check yourself, and this is kind of fun because you see it actually happening. You're like, oh wow, I can really check myself with this. Okay, so with this, we're just going to find the inverses first. This portion is checking. Okay, so here, let's go by the steps. Replace f of x with y, so y equals 3x minus 1. Interchange the x's and y's, so switch the x's and the y's. So my y's become x's, and my x's become y's. And then I want to solve for y. So remember, if I'm solving for this y, we had a lot of practice on this in what, section 1.3, like back in unit 1. We had to solve for variables. So here, remember, we want to take this negative 1. So since it says subtract 1, I'm going to add it to both sides. So when I add it to both sides, I've got x plus 1 on the left-hand side, and then 3y left over. Okay. If I go ahead and solve for y, since it says 3 times y, You divide 3 on both sides. And notice, it's over the whole entire thing. So make it easy on yourself and just, divide the whole thing by 3 and don't split it up. Don't put it in mx plus b form or anything like that. Make it easy on yourself. Leave it like this. Okay. So you actually have this inverse function now. You have an inverse where x plus 1 over 3 is the inverse of this 3x minus 1. So I'm going to go ahead and claim it as my inverse. And I'm going to say, oh, well, my f inverse of x equals x plus 1 over 3. Okay. So notice that my regular function had a 3x minus 1. Now this one has a x plus 1 and then divided by 3. And if you wanted to do a quick check for yourself for at least just one number, what if you had plugged in a 0? Say if you had x and then f of x, and you plugged in a 0. Well, if I plugged in the 0 into this, it would be negative 1. So this means that for my inverse function, that I know that my x's and y's switch, so this has to be my x in my inverse function. So if I plug in this negative 1 here, I should get 0 out of it. And if I plug in a negative 1 in this, I got negative 1 plus 1 gives me 0. 0 over 3 gives me 0. So it works for at least for one point, but we're going to see in a moment that it works for every point. But I'm going to hold off on that part of the checking, that number 4 part, until we get comfortable in finding the inverse first. Okay, so for this one here, notice this is a cubic function. We know what a cubed function looks like. And the best way to describe this is it looks swirly. A lot of times people say that. So it's your swirly looking one. Remember, it's one of your basic graphs and it goes to the point 0, 0, and 1, 1. But notice, I can draw a horizontal line through it all day long and it's 1 to 1. Therefore, it contains an inverse. So now that we know that it has an inverse, or it can have an inverse, then we have to find it. And y'all remember, just kind of a side note here, remember if you have an x squared, to get rid of that squared, you would take the square root. If you had an x cubed, to get rid of that cubed, then you would cube root and you would have x. Okay, so this is x cubed, so you want to take the cubed root. Okay, so first things first though, we have to go by our steps. So our first step is just change f of x to y. So that's exactly what I'm doing. I say y equals x cubed minus 1. And then adding 1 to both sides, y plus 1 equals x cubed. And I still have to solve for x, but remember what undoes a cubed is a cubed root. So if you get a cubed root in the beginning, then you just cube both sides. But this is a cube, so I'm just going to go ahead and take the cubed root of both sides. So this 3 and that cubed root are gone. And y'all, you know what I forgot to do? Who sees it? I forgot to switch my x's and y's. So you can still do that. You can switch the x's and y's on either the second step or third step. It doesn't matter. It's still the same thing. So let's do this again. So I'll show you. It's the same exact thing. So switching the x's and y's, if you wanted to go into steps in order, you can have x, you can have y. Again, adding 1 to both sides, x plus 1 equals, and then y cubed. Note, to get rid of the cubed, I take the cubed root, not the square root, but the cubed root. So those cancel out, leaving me with my inverse function. So my inverse function here, I'm going to claim this as my inverse function. the cubed root of x plus 1. Okay. Okay, so now that we've found our inverses mathematically, let's go to step 4 and see if we can make some sense from all of this stuff up here. First of all, the f of f to the negative 1 of x, notice that word of a lot, it's the composition of. It's the composition, it's the same composition that you guys would use from section 2.6. Okay, the same composition. So this means, what this says that here, if you notice, actually let me erase this so I can point to stuff. So here if you notice that this inverse is on the inside of this function f there, okay? And notice that this function is on the inside of the inverse. So what this is saying is that if you were to plug one function into the other, then you should get x out of it. And I mean literally, you should get x. Once everything is simplified, you should get x out of it. So this is how I'm going to check. Okay. So if I take, and we'll do, and I want to tell you though, look, they have two of them here. You don't have to do both. Just one will work. So if you get used to just doing one a certain way all the time, like if you are just the type of person who likes the same procedure every single time, you can say, well, I like plugging in the inverse into the regular function to check. And I'm going to do that every single time. That is perfectly fine. If you're a person that says, you know what, I like to take the regular function and plug it into the inverse every single time, that's fine too. So again, you don't have to do it both ways. You only have to do it once. So on this first one, just because this one is first, I'm going to go ahead and plug this into our regular function, and we should get x out of it. On the next one, I'll do the opposite to show you that you should still get x out of that as well. Okay, so in order to check, I am just doing exactly like it says. I have f, and then I'm plugging my inverse into that. Okay. So f of, and that's my inverse, which is x plus 1 divided by 3. And so I'm taking all of my x plus 1 divided by 3 and plugging it into that x. Okay, so I've got 3. So what that function does is I have 3 times something, and then I subtract 1 from it. So I take all of this stuff and plug it into there. So I have x plus 1 divided by 3. And I'm sure everyone is looking at this saying, well, I don't see it just equaling an x yet. But what's really cool about this is you have things that will cancel out. Notice that this is what, 3 over 1. Those 3's are canceling out, leaving me with x plus 1, and then minus 1. And then plus 1 minus 1 gives me just a simple x left over. Because that we plugged one function into the other, and we got x out of it, then that means that we got the inverse correct. That in fact, x plus 1 divided by 3 is the actual inverse of 3x minus 1. Okay, so let's try the next one in the opposite way. This time, to check, I'm going to take now the regular function and plug it into this x, into this inverse. So I've got, just writing this out, f of negative 1 of f of x. We know that f of x is all of this stuff here. So I've got x cubed minus 1. And so what this inverse does, it says I'm adding something by 1, and I'm taking the cubed root of the whole entire thing. So I've got the cubed root, don't forget to write your 3, and you have the space, and then you have a plus 1. So in this space has to go all of this stuff, and he has to go in that space. So we have x cubed minus 1. So y'all, in simplifying, remember PEMDAS. Please excuse my dear Sally. So parentheses, and then exponents, and so on. So we've got here working our way from the inside out. Notice that this negative 1 will cancel with this positive 1, leaving me with a cubed root and an x cubed. And remember that those cancel each other out, leaving me with a simple x. So notice, once again, we still got x to it. Okay? Now, I want to caution y'all on a couple of things. Don't do this. What you are about to see. Don't be that student who does this. Notice that I have steps here. I have, hey, I canceled out one thing, and then I canceled out the other, and then I got x from it. So as a student in a math course, you need to be aware that you have to cancel out things properly. Because right now, the x cubed and the cubed root do not cancel out. You have to know the proper order of operations, right? So don't be the student that does this and is like, oh, okay, I got my f of x, and I plugged it into my inverse, and I got this. So I'm going to say, okay, cubed root x cubed minus 1, and then I've got this, and then, you start doing this. Oh, that cancels, and then you have x. Don't be that student. Remember to show your steps, okay? So just keep in mind that order is going to matter in this. So you need to show each step all the way down till you get an X, okay? Just so you know. So order of operations matter. Show steps. Only cancel out one thing at a time. That's your best bet to get full credit for all these. Okay, let's see. What else do we have? Mixed up. All right, so this is where a lot of times there's a little bit of confusion with some things. So for y'all to fully know about inverses, and yes, this is a more complicated one. Beforehand, notice that we never had a function that was squared, right? We had one that was raised to the first power, like a linear function, or we had a cubic one. We have not done a square yet. And here's the reason why. This here, so if we just take this constraint out of it, and let's just, I'm just scratching this out for now. I'll bring it back, I promise. So if we take that constraint out of it, we have this. Notice it's just a basic graph of x squared, and it had moved over to the right by 1 unit. So we have the point 1, 0, and then we have the point 2, 1. And that's what that graph looks like. Okay. So when it says find the inverse of this, meaning that, notice that when we graph it, can we say that this is 1 to 1? Does it pass the horizontal line test? No, it doesn't. So what happens with this is that we can't find the inverse because the inverse is not going to exist because it is not 1 to 1. Now, here's the kicker. If I bring back this constraint, I'm bringing back the constraint that I'm only looking for x's that are greater than or equal to 1. Well, here's 1, and I'm only looking for x like this way, for all the values this way. So notice all my points to the right are here. That means that I'm not even taking into consideration anything below 1. I'm including 1 on up to infinity, but I'm even taking that part out. So this is the graph that they're referring to. This is 1-to-1. So notice that this is 1-to-1. This, I can have horizontal lines through it all day long, and it won't cross but more than once. Sorry. It won't cross except for exactly one time. Okay, so it does have an inverse, and therefore you can find the inverse. So let's go about finding this inverse. Okay. All right. So from here, do our regular steps. F of x, change that to y. So we have y equals, and then x minus 1 squared. Do the inverse part, which means switch the x's and y's. So we say x equals y minus 1 quantity squared. And then I'm going to solve for y. Okay. So when I solve for y, I have to get rid of this square first. And we know to get rid of that square, I have to take the square root of both sides. The only thing is that when you take the square root of both sides, you have to remember that you have a plus and a minus. Okay, so I have to choose which one I'm going to have here as my answer, because at this point, I'm not sure. Okay, so let's think about this. That these are all for x's that are positive, right? And we're looking at the right side of the graph. So if I were to draw this, remember I have to use the fact that I know that it reflects over the line y equals x. So it's probably going to look something like this, or at least it should look something like that. Okay. So just looking at this graph here, note that this looks like your regular square root. It doesn't look like a negative square root, because remember, a negative square root, if you recall back from section 2.5, that negative square root, that negative portion to it, reflects it across the x-axis. This is not reflected across the x-axis. Notice that this is a regular square root function. It goes in the same shape and the same curvature, the same characteristics, right? It just happens to be moved up 1. So we can say that this is the positive. So we want that to be positive. So we want to take this away. So we have, and I'll go into more detail on it, no worries. So we have the square root of x equals y minus 1. And then we have, still solving for y, whoops, said y, and I wrote y. So the square root of x, and then we add that 1 over to the other side, equals y. So this is my inverse function. And it makes sense because I got the square root, and notice it's raised up 1 from that 0, 0. So that works. So we're going to claim it as our inverse function. Okay. So now here's the deal. It says, what if the function were defined for x less than or equal to 1? What would be the difference? Okay, so if you had the x less than or equal to 1, this means that you would have, and let me take a peek at the function again so I can write it properly. So this is saying the same exact function, except now the constraint to it is all x's that are less than or equal to 1. So you have x minus 1, and then squared, and then you have x is less than or equal to 1 this time. So in this, much like the other one, this portion here is not describing the right-hand side of the graph like the other one. This down here is describing the left-hand side of the graph. So this starts out at 1 over here on my x's and goes over here. Okay. So now, what we're going to have to do is that notice that even if I drew this, and I was like, well, I want to choose the positive one because I'm just comfortable with it. Well, check this out. The inverse is not going to look like this. Notice that if I drew the line here, it wouldn't be symmetric, right? It doesn't look like it would be reflected across the line y equals x. So the positive is not the one that we want. And I'll show you why. When we solve for this, like we did before, we got to that point to where we had, what is it? We had, well, let me just go ahead and try this. We got y equals x minus 1 squared, quantity, and then we switched the x's and the y's. And we were solving for y. And so when we took the square root of both sides, remember we got a plus or a minus. Well, we kind of know now just from the picture alone that we're not going to be choosing the plus. We're going to be choosing the minus. And so this means when I move that 1 around, I'm going to have negative square root x equals, whoops, I didn't move my negative 1, did I? Negative square root of x plus 1 equals y. So notice what happens with this. This means that you have, a regular function x, which looks like this. Okay. The negative part to it reflects it across the y-axis, and this plus 1 moves it up 1 unit. So this is the graph that we kind of want to place up here. So thinking about it, we've got, it starts off, oops, I reflected across the y-axis, so the x-axis. Hold on a second. Let me redo this. Okay, so we've got a square root x, everyone's familiar with, like we've already stated, looks like this. And then we've got the negative portion to it, so it reflects it downwards, right? So really we've got this part. So drawing this, it goes in the downward motion. And then here we go, we're going to be moving it up 1. So this whole negative x plus 1 looks like this. So when we draw this, it's going to look like that. Okay, so that our line y equals x, notice it reflects across it. So if we were to fold that, it would look exactly like the other side. Okay. So with this huge long explanation about what to do and which to choose, positive or negative, if it says the left side, choose the negative. If it says the right side, choose the positive. Okay. So again, if it says the right side, choose the positive. If it says the left side, choose the negative. And y'all, this is only for things like squares, or to the 4th, or to the 6th, or anything like that. Okay? You have to realize that you've got, left-hand side versus right-hand side. Because if it didn't have a constraint on it, you wouldn't even have an inverse. Okay. Okay, great. So let's see what the next slide contains. Of course, you're always going to get one of those lovely challenge problems, right? Okay, so here it says find the inverse of f of x. It gives you that function. And so if you find the inverse, then you have to check for it. Okay, so now I want you to know that I'm hoping y'all all try the bonus problem tomorrow, because this is a lot like the bonus problem here. So if you get that, then you get some really good points for knowing how to do that on your homework. So remember that this is extra credit. This is due day of unit 4 test before the start of okay. So definitely play around with that and try it out. They're kind of neat, fun things to do. Anyways, I hope that this was a good video for you guys, and if you have any questions, please feel free to send me an email or ask questions in class, however you like to get some of these things answered so that you can move forward and make a great grade on the next test. Have a lovely evening.